Okay, that's cool.
Happy to close the school. Anyway, so last time I reviewed celestial OP for you, and I showed you that you can construct, at least for the purposes of the MHV amplitudes, you can think of a graviton celestial operator. You can think of a graviton positive helicity graviton state to be dual to some celestial operator O plus plus Z kappa tilde 1 dot kappa tilde 2 dot. And for the purposes of the MHV amplitude or just the positive helicity sector, you could take this operator, you could take an ansatz where this operator is real analytic in the kappa tilde, complex analytic, sorry, we are complexifying all our momenta. So what I did was I basically did what I called a soft expansion. Sum over m n greater than equals 0. Basically, Taylor expanded in the kappa tilde components. Then I extracted the collinear limit of the scattering amplitude, and I basically made this argument that, just to repeat in pictures, if you have a scattering amplitude of gravitons, and if this is a affine coordinate patch of your celestial sphere, of the Z sphere, then if these two null momenta become collinear, then the corresponding insertions on the affine patch come close together, and you would expect some sort of an OPE limit in the dual CFT. And then using the collinear behavior of amplitudes, I sort of motivated this celestial OPE. Tilde I alpha dot. So don't confuse these indices with the particle index I. Each of these has an alpha dot index, but which I'll suppress. O plus plus Zj alpha tilde j was square brackets 1 to square brackets ij over zij. So this is Zi minus Zj times collinear, like sum of the two gravitons. So since it's an OP, it's expanded around Zj, kappa tildes are added together. And from this, you can expand both sides in such a Taylor expansion and read off the OPs of the chiral currents WMNs. And so for the WMNs, you find this beautiful W infinity loop algebra OPE. WP, Q, WR, S, Z prime went like PS minus QR over Z minus Z prime. So that's your structure constant. That's the singularity. W, note what comes out has a shift by -1 and Q plus S minus 1. So now can we build some sort of simple model using twistor space that can reproduce this OPE? To understand what model we have to build, yeah?
So in the prior lectures, one of the messages he's trying to pass is that just because we have local bulk theory doesn't mean that on the celestial sphere we're going to have local operators. But if we get an OP of this form, which is local OP, can we conclude that the operators corresponding to graviton states are local operators on the celestial sphere?
That's basically what I'm assuming, at least for these soft operators, that these are local. It's not clear at the moment whether it's an assumption. Yeah.
Are you assuming that to write the OP, or does the OP fall for someone else?
Oh, the OP can be written for non-local operators as well.
And it looks like this.
Yeah.
So this form of just an expansion in terms of. Oh, you mean the operator on the right itself might not be local? So
Yeah, it's to be honest, still an assumption. What I'm going to give you is some kind of one sort of toy construction of this in terms of some fundamental local operators. But of course, yeah, It is an assumption, I can't lie about that. Anyway, so just to give you some geometric interpretation before we go full twistor mode, what is WPQ? So I said the name W1 plus infinity in the last lecture. So this OP was originally discovered by Strominger quite recently. I didn't note down the year in my notes, unfortunately. Well, last year, sorry. And the geometric interpretation of this OP is as follows. Basically, can you try to find some kind of classical object which has these structure constants, some kind of algebra? We want to find some kind of geometric interpretation of these structure constants. And indeed, there is a very nice classical algebra whose loop algebra gives you exactly this kind of OPE. So,
sorry, can you briefly tell me what a loop algebra is?
I'll first tell you what the classical algebra is, and then I'll tell you how you construct the loop algebra. So basically, the classical algebra W1 plus infinity. Oh, well, just to say loop algebra, it just means level 0 Kac-Moody algebra of some Lie algebra. I don't want to keep saying level 0 Kac-Moody again and again. So W1 plus infinity is the algebra of symplectomorphisms of canonical transformations. I didn't realize how long this word will be. Symplectomorphisms of a two-plane. So you can take R2, I'm going to take C2, so some holomorphic two-plane. And how do you see this? You basically take C2, and quite suggestively, I'm going to use coordinates mu alpha dot on my C2, so mu1 dot, mu2 dot. This is not yet a twistor. Just take some C2 with holomorphic coordinates mu1 dot and mu2 dot. And now endow it with the obvious Poisson bracket. So if you have two functions f, g, functions of these coordinates mu's, you can take them to be holomorphic functions. That's all I'm going to need for this lecture. The natural Poisson bracket is partial f by partial mu1 dot, partial g or partial mu2 dot minus the other way around. So you take f and g holomorphic in mu alpha dot for our purposes today. If f and g are holomorphic, okay, oh, that's a nice compact way to write this using the Levi-Civita symbol epsilon alpha dot beta dot, partial f by partial mu alpha dot, partial g by partial mu beta dot, which I'll use from now on. The geometric interpretation comes from the fact that if you have, if you just consider holomorphic functions of mu, f of mu alpha dot, then you can expand any such holomorphic function. So holomorphicity is complex analyticity. So you can expand this in a way that's quite reminiscent of that Taylor expansion as mu1 dot to the m, mu2 dot to the n over m factorial, n factorial times appropriate derivatives of that function, of course. Partial mu1 dot to the m, f at the origin. Okay. So basically, the functions mu1 dot to the m, suppose we define Wmn as some classical objects. Now these are not functions of z, these are just the classical objects, mu1 dot to the m, mu2 dot to the n. Consider these objects. You observe that these objects now form a basis for the holomorphic functions. And very nicely, if you consider the Poisson bracket of these basis functions, you reproduce exactly those structure constants, unless I have made a sign mistake. Let's see. You compute this Poisson bracket, so you get partial by partial mu1 dot of mu1 dot to the m, mu2 dot, sorry, p, mu2 dot to the q, p by d mu2 dot, mu1 dot to the r, mu2 dot to the s, minus the other way around where you exchange p with r and q with s. Now, can someone quickly tell me what the answer is going to become? When you differentiate this basis element with respect to mu1 dot, it acts on just mu1 dot to the p. That brings down a p. And when you act with mu2 dot on this, it acts on the mu2 dot to the s. That brings down an s. And then you're left with mu1 dot to the p minus 1 from here and r from there. And mu2 dot to the q from here and s minus 1 from here. Minus the other way around where you exchange p with r and s with and q with s, or s with q, so rq, times, if you exchange p with r, this doesn't really change, so you get the same object. And so you get exactly ps minus qr. Now you realize that this object is the basis function w p plus r minus 1, q plus s minus 1. And this is the same object. So we basically realize a classical analog, just as a Lie algebra, we realize a classical analog of this OP through the Lie algebra of these basis elements that generate holomorphic functions.
You just guessed that we take that form to see if you can reproduce the algebra, is that correct?
Oh, that is not my guess. That's like known for ages.
Yeah, I mean,
But somebody
is there any other reason why you guessed W to give that form? When you say
that is the most natural. No, that is how it was originally defined anyway.
Okay.
Here we will guess that we can use that representation for our purposes by thinking of mu as the twistor coordinates. That will be the guess. But yeah, that it's quite cool that how we sometimes randomly discover the same mathematics in completely different corners of physics.
So here, is this still the algebra? I don't see any brackets.
So no, here, okay, there it's just a Lie algebra. It's an infinite dimensional Lie algebra because the generator is mu1 dot to the m, mu2 dot to the n, like there are countably infinitely many of them. Here, I'm going to associate a loop algebra, which is basically the level 0 Kac-Moody algebra. Like whenever you have a Lie algebra G, you associate a Kac-Moody algebra by basically just defining currents, W, P, Q of Z in this case. So I should say, let's use, whenever I have a W infinity algebra, W1 plus infinity, where the 1 corresponds to the central element when m and n are both 0. So that's just the basis element 1. This corresponds, 1 corresponds to W00 equals 1. And then I'm going to define its Kac-Moody algebra at level 0, which is usually denoted in the literature as a loop algebra, L of W1 plus infinity, by basically instead of replacing the WPQ classical generators by some currents, which have exactly that OPE. So that's how you pass from a Lie algebra to its Kac-Moody algebra at level 0, a loop algebra, so to speak. You can also define it somewhat more classically by giving these currents a mode expansion like you do in CFTs. So you would write something like K in Z, all integers, Z to the K plus 1 times some modes WK, WPQK. And the idea would be that the modes WPQ naught would satisfy the classical commutation relations of the W infinity Lie algebra. PS minus QR. And that's, hopefully, you have seen this in courses on string theory or something, or basic CFD, how you pass through, how you define Cosmology algebras. If anyone wants me to describe this in more detail, I can tell you. But this is like exactly the same thing, just that instead of a finite dimensional Lie group, the gauge group, we are dealing with an infinite dimensional Lie algebra, W1 plus infinity, and then defining its Cosmology algebra.
These W's,
Like
they're just the basis of holomorphic functions on C2.
Yeah, exactly. Then, yeah. And then at the level of this, there is some one-to-one correspondence between the zero modes of these currents and these holomorphic functions and so on. How do we realize this on twistor space? Now we have, yeah, okay. So now our job is to find some sort of simple model for celestial CFT that can reproduce these celestial OPEs. And it turns out that this simple model can be now motivated by this realization that this soft OPE algebra is exactly the algebra of holomorphic functions on a two-plane. Because now I'm going to say that my two-plane is exactly the two planes of the mu's in twistor space. So recall that twistor space was an open subset of CP3. So twistor space PT was the set of scaling equivalence classes of twistors. This first two, so 4 component objects, his first 2 components were mu alpha dot, last 2 components were lambda alpha, and taken up to overall scalings, modulo the assumption that the lambda alphas were never simultaneously 0 because they were meant to be some sort of coordinates on a chiral half of the complexified celestial sphere. And what we do, now it's simple how to build a model. What we're going to do is build a sigma model governing maps. Okay, this is not completely obvious. It's obvious to me because I've been working on this for a while. But let me try to convey the idea to you and ask me questions. I promise it'll work, though. It's quite cool, actually. So we have to build a sigma model. Okay, why do we have to build a sigma model? You have come across quantum mechanical models where you have some time direction and that maps into some space, and then you realize some sort of symmetry algebra of that space in terms of commutators, with basis generators being written in terms of the coordinates of the target space. We're going to do something similar here. Sigma model governing maps from a Riemann sphere, which for all intents and purposes will be our celestial sphere into PT, but with a slight rigidity to it. So suppose this is PT, and suppose I draw my CP1 as a projective line, and the lambda alphas run this way. Let's take this to be the twistor line dual to some coordinate x. So you can take it for simplicity to be the twistor line dual to the origin of space-time. So L naught, this, which is all the same as CP1 topologically. And then you have C2 planes. So twistor space looks something like a cylinder with C2 cross sections. And the mu alpha dot are coordinates on these C2 cross sections. So each of these is a C2 plane, and mu alpha dot is a coordinate system on each of these cross sections. So what I'm going to do is, okay, yeah, this is very natural. If you had just a C2, then you would get the classical Lie algebra. If you want to get the loop algebra, you want an extra Z direction. How do you realize it most naturally? By fibering these C2s over a Z direction. And that's exactly what twistor space accomplishes. You have some lambda alpha. You can take affine coordinates, lambda alpha equals 1 Z, and now build a sort of model that governs the embeddings of CP1 sort of along this direction in a way that's parallel to this direction, so that the coordinates on this embedding are basically still z. You can sort of coordinatize this embedding of CP1 by still z, and the heights of this embedded CP1 is given by some functions mu alpha dot of z as you move along z. So that's the idea. It's, huh? Yeah, it's, sorry, I was just trying to give you the intuition. Now I'll write the equation down and that will be more clear.
Is it obvious that twistor space is like a cylinder of this type from what we did?
I will not say it's obvious because it does take a little bit of a while to sort of, you know, but yeah, it is sort of, it has that nice structure. So twistor space we defined was the C2 coordinatized by the mu's times the C2 with coordinates lambda alpha, but you remove the origin of that C2 modulo the overall scalings. So basically this C2 is sort of separated out, and for each value of lambda alpha you have one C2. So this is basically the geometry, how you have to imagine the geometry. I didn't say it before because this was the first time I was going to need it. But yeah, basically once I've shown it to you, you can't unsee it, hopefully.
So it has some C2 bundle over C2.
It's exactly that. If you want to know, this is the bundle O1 plus O1 over CP1. Huh? O1 is the dual to the tautological bundle, so stuff that scales positive, like with degree 1. Okay. So mu alpha dot, as you move in lambda alpha, mu alpha dot scales the same way as lambda, so that's why it's degree 1 section, so it's like O1 plus O1. Anyway, but that's the picture that you should have in mind. You're going to build a two-dimensional CFD, which is going to be a sigma model governing maps that embed these projective lines in that fashion, in a way that sort of, the line is parallel to the base CP1, but its height is going to be the field of the model. And that's exactly the kind of structure that I need to reproduce the celestial OPE. So what do? You basically build a sigma model with fields, well, 2D sigma model, with target PT, goes, and fields, well, yeah, target PT up to demanding that everything is parallel to the baseline, with fields. So the only non-trivial fields of the model are the perturbative modes mu alpha dot of z. So basically, I'm going to use the same symbol mu alpha dot for the function that defines the height, rather than, because mu alpha dot is the coordinate along the C2, along the normal directions. So I now have a field, a chiral field, mu alpha dot of z. I'm going to assume it's a chiral field. And now I'm going to give it an OPE. What's the most natural OPE? As we saw, or as you've seen in Prahar's talks in higher dimensions, you get 2-point functions of quantum field theories from the natural symplectic, from the Poisson bracket that you have, that you turn into a commutator, and then you get a 2-point function of your fields in your quantum field theory. We do something similar. You basically take the God-given Poisson bracket on C2. So this Poisson bracket, if you have a holomorphic function f, but now an arbitrary function of lambda and lambda bar, and g, holomorphic in f, arbitrary, well, I can use z and z bar now. I'm just going to work in this affine patch, where if you like, z is lambda 2 over lambda 1, so it doesn't scale. That's just a stereographic coordinate on the Riemann scale. I use this Poisson bracket, and that tells me to set this to equal the God-given Poisson bracket on C2 with respect to the standard Levi-Civita symbol that we've been using all along. And now, when acting on the generators mu alpha dot and mu beta dot as classical coordinates, this Poisson bracket just gives me epsilon alpha dot beta dot. And this is now what I'm going to turn into some sort of OPE. So in higher dimensional QFT, you take the Poisson bracket. So this is very similar to quantum mechanics. If I was doing quantum mechanics, I would turn this into a commutator in QM, just like how you have maps in standard quantum mechanics. You have maps from the world line into configuration, into phase space x comma p, and you turn the coordinates of phase space x comma p into operators, and you take the Poisson bracket on phase space, which was x p, and you turn that into a commutator, and you set this to 1. I'm going to do something similar. Had I been doing quantum mechanics, I would have taken this Poisson bracket and turned it into a commutator. I'm doing 2D CFT, so I'm going to turn it into an operator product expansion. So instead of that, I'm going to do mu alpha dot of z. Maybe I can, let me write that on a different board. This is the fundamental OPE. Basically give it the OPE mu alpha dot of z, mu beta dot of z prime goes as the Poisson bracket, the symplectic 2 form, divided by the requisite singularity, plus regular terms that we don't care about because our fields are all chiral. So this is the most important thing. What I'm going to do is I'm also going to put an h bar like you would do in typical quantum mechanics. I assure you, you can set it to 1 and everything still works out. It's just a loop counting parameter that is useful for purposes. So, h bar is a loop counter. Okay, now we're in business. Once you have this idea, once you have had this idea, you can immediately imagine what composite operator to write in terms of these fundamental operators mu alpha dot of z's to reproduce the W infinity loop algebra OPE. So can someone tell me what composite operator I should write in terms of the mu's, just from the guess that I made for in the classical case, which I rubbed off. So in the classical case, I use mu1 dot to some power, mu2 dot to some power as a basis. I'm going to do the same thing here. Yeah. So in the sense of a 2D CFT, you have to normal order those fields. Yeah. So I'm not going to focus too much. It's all like just nothing special, just standard normal ordering. So I can put a normal ordering symbol for you if you like, but I will never write it again. Yes. mu1 dot to the p, mu2 dot to the q, normal order product evaluated at z. And that's going to be a basis of my fields in my 2D CFT. And now immediately compute WPQ of z, WRS of z, primed at z, mu1 dot to the r, mu2 dot to the s z prime. How do you compute this? You basically take big contractions. In the classical case, you take nested commutators. Here you just have to take big contractions. And what I'm going to do is, modulo having space. I'm going to keep only the single wick contraction term, so only the order h bar term. Oh yeah, this is very much just the free theory. That's just the free OPE, yeah. You can write an action for it if you like. The action is just going to be integral dz, well, d2z, mu alpha dot, partial z bar, mu alpha dot. That's the free action, yeah. Anyway, if you compute that OPE, you will get, by doing a single contraction, so you do a single contraction between mu1 dot to the p, mu2 dot, mu2 dot to the s. This contraction, after a single contraction, it differentiates this once, and you get exactly the single contraction between mu1 dot and mu2 dot, which is h bar over z minus z prime. So this is at z, this is at z prime, times mu1 dot to the p minus 1, mu2 dot to the s minus 1. And similarly, there's another case where you take a contraction between mu2 dot to the r and mu1, what did I write? You take a contraction between this and this, or the other case is when you take a contraction between that and that. Okay? But take just one contraction, and the OP that you find at the end of the day is h bar over z minus z prime ps minus qr times exactly mu1 dot to the, well, okay, now the remaining stuff you normal order again, and you just multiply them throughout, so you get exactly p plus r minus 1 q plus s minus 1 plus order h bar squared terms. So the idea, or the hope, is that to order h bar, this is generating the tree level OPE. You can, what you can do to get rid of the h bar is just rescale the WPQ currents by 1 over h bar. And then you would have two factors of h bar squared coming from each of the WPQ and WRS. Should cancel one of them here, and this object would now be W p plus r minus 1, q plus s minus 1, evaluated at the second point. The hope, so to speak, is that to leading order in h bar, this is generating the tree level contribution of celestial CFT. And what happens at subleading order in h bar? We don't know. Maybe one of you can find out. But this is like the simplest model that you can build. And we named it a Twistor sigma model for reasons that I described earlier. And you can find this in some papers by, well, Tim Adamo, Lionel Mason, who's my supervisor, and myself. Some recent papers. I think it has W1 plus infinity in its title, as you should always do. Okay. So that's the simple model that sort of reproduces the soft celestial OPE. Oh, I'm already late. No, okay, I'm not. Sorry, got confused. Yeah, we started at 10:30. Okay. So now, let's see if we can reproduce the hard OP. Any questions about this procedure? I'm hoping this is like you've seen this level of 2D CFT, but you haven't, you can ask me. Okay. Ask me in the discussion session. Now let's see if we can reproduce the OPE of the hard operators. So yeah, I guess at some level our hope is that this is the leading term in the action of some celestial CFT, the celestial dual of GR, at least in the self-dual sector, or maybe also as applicable to MHV, graviton amplitudes. But that's of course work in progress. Let's see how to reproduce the OPE of hard operators. For hard operators, you recall the definition of the, well, I recalled it at the beginning of this lecture as an infinite Taylor expansion in the capital components. Now I had WMN here of Z. What I'm going to do is replace this WMN of Z by mu1 to the P, mu2 to the Q. Now I'm going to remove that factor of H bar by just putting an H bar explicitly here. Or, oh no, sorry, I won't do that. I suppose it's the same. It's needed. Okay, yeah, so now simply take this WMN and use the ansatz that I have bracketed here. So you plug in that ansatz for WMN, and you get mu1 dot to the M, mu2 dot to the N to Z. Now these are just numbers, so you can bring them inside the normal ordering if you wish, and you can sort of combine them with the mu's, and you get one over m factorial, n factorial. Okay, take the 1 over h bar outside. Inside the normal ordering, everything commutes anyway. So you get mu1 dot kappa tilde 1 dot to the m, mu2 dot kappa tilde 2 dot to the n. And now you see that you can, this is basically just a product of two exponential sums. So this exponentiates into e to the I mu1 dot kappa tilde 1 dot plus I mu2 dot kappa tilde 2 dot, evaluated at Z after normal ordering. What is mu1 dot kappa tilde 1 dot plus mu2 dot kappa tilde 2 dot? It's exactly what I would call square bracket of mu with kappa tilde. So mu of Z kappa tilde. So this is my ansatz for the hard fields. For a positive helicity hard graviton operator. Again, just to repeat, I'm not going to deal with mixed helicity OPEs as I discussed and as we've been discussing over the course of the last few lectures. Mixed helicity soft theorems and OPEs are still under investigation. I can use that one. Okay, so now can we derive the hard graviton OPE? And by now it should come as no surprise that you'll again get a Poisson bracket coming in, and it will all work out. So maybe I can give this to you as an exercise. Show that the OPE between mu of Zi I, and this is just short for mu alpha dot of Zi kappa tilde I alpha dot. No ordered. I mu of Zj j normal ordered. 1 over forget about the h bars for now. They all work out anyway. So to leading order in h bar, you should show that. Okay, we just put that here. This just becomes. Okay, I can just show it. It's not that hard. So when you take the Poisson bracket, when you take the OPE, you have to differentiate this thing once, this thing once. That just gives you the Poisson bracket because of the epsilon alpha dot beta dot that accompanies the OPE. So you get h bar over z minus zi minus zj times the Poisson bracket of mu mu kappa tilde I, let me just write it down explicitly, mu kappa tilde j evaluated as zj times normal ordered e to the I mu of zi I this I, sorry, evaluated at zj now, mu of zjj, this Poisson bracket, basically you have, this thing is just mu alpha dot kappa tilde I alpha dot. You don't need to rewrite it, but I'm just showing you what it is. So mu beta dot kappa tilde j beta dot. And now if you differentiate mu alpha dot here, mu beta dot here, you just get epsilon alpha dot beta dot kappa tilde I alpha dot kappa tilde j beta dot. I think I did do a sign mistake, but up to that, this is just going to give you, I think, minus ij over ij, zij. You can sort of have an I everywhere if you, sorry, there's an I that comes down when you differentiate this, so that's an I squared here, so that turns this into a plus. Everything works out. You have an h bar squared, which cancels that, plus order h bar, higher order in h bar. So leading order in h bar, you get exactly this structure. You get the structure by differentiating the mu's and then contracting the resulting kappa tildes. The zij is from the OPE times a hard graviton at zj. And now you notice that mu of zj I plus mu of zj j is nothing but mu alpha dot of zj times kappa tilde I alpha dot plus kappa tilde j alpha dot. So you end up summing over the kappa tilde part of the operator. And you exactly reproduce the operator, sort of composite graviton operator that flows on the right hand side of the OPE. And this sort of gives you the dynamics that you observe in the graviton scattering amplitudes from first principles, so to speak.
But if I insert this in a correlator, then there is a conservation of k that I have to, because there is an exponential, right? So I have to impose some charge conservation condition, right?
If I remember correctly, that turns into momentum conservation.
Goes into momentum conservation.
Yeah,
Okay.
yeah. I mean, there's a little subtlety. There are a few subtleties which are discussed in the paper. Up to that, it does give you the MHV graviton amplitude on the nose, and the exponentials have some zero modes which give you the charge conservation. It becomes momentum conservation. And that's it. That reproduces all the observed celestial OPE in the like helicity sector for you. So.
I have a question. So probably very stupid. Can you remind me what happens with the double wick contraction?
The double wick contraction would just give you like p times p minus 1 maybe on one side and q times q minus 1 plus order h bar squared, of course. We just don't know what that algebra is.
Okay.
Maybe Simon knew because he's working on the symplectron thing, but he ran away. So it's not yeah. It might be something that knows about loop level positive helicity graviton amplitudes, but I am very lazy, so I haven't looked at them. Yeah, we will explore them in the future. The other possibility is that it's somehow related to sort of brain back reaction effects like in standard holography, but I'm not entirely sure because I was talking to you yesterday and you said that when you compute subleading terms in the OPE, so whenever you have non-planar contributions in standard super-Yang-Mills, you get some multiple wick contractions but arranged in a non-planar way. You would get loop level terms in the dual gravitational side, in the bulk side. So my expectation is that if we can embed this whole sigma model into as a string theory and then show that there is a back reacted geometry where there's some sort of gravitational dual, then order h bar, higher order in h bar terms would probably compute loop corrections in the back reacted, in self-dual GR on the back reacted geometry. That, in fact, is still a work in progress with, I'm doing some work on that with Kevin Costello and Natalie Paquette. So we're trying to see exactly what back reacted geometry that gives. But yeah, that's for another day. Let me quickly tell you any other questions? Otherwise, I'll go to the Yang-Mills case quickly. Good, very good. So, I forgot to tell you about the connections to supertranslations and superrotations, so let me quickly mention that. Basically, what happens is that W naught naught of Z is a central element, so we forget about that. It doesn't have any connections to any usual soft terms. I told you that all of these are soft modes, but exactly which soft modes they are. W1 naught and W naught 1 correspond to supertranslations. If you want to know exactly how, you can read Strominger's papers, and it's references therein, I guess. Guevara's papers and some other related papers. So W2 naught 1 1 and naught 2 are related to superrotations, and you can actually check that their subalgebra is an SL2C algebra. You can check that their mode algebra is an SL2C loop algebra. And these happen to be superrotation soft modes. So basically, delta equals, so these have weights delta equals 2, 1, 0, and so on. These are exactly the operators that Prahar was writing down. So weights delta equals 2 in a Mellin basis, in a Mellin sense. These are all conformal primaries, even though I extracted them from momentum eigenstates. They're still conformal primary with these weights. And the weights then immediately tell you that these soft modes are related to supertranslations, and the delta equals 0 ones have to be related to superrotations. And you can check out the papers for more fun details.
So there's no interesting soft theorem associated to the central element?
I think, yeah, it's just 0 or something. Yeah, I think I did try this, and it just gave me 0 or something.
What about all the other tables?
What?
All the other tables?
The other ones? Yeah, they don't organize into soft theorems. To my limited knowledge, I have tried to organize them as some sort of universal soft prefactored times, an amplitude of lower one less particle. One would hope that at least at MHV degree they might, but they don't. My expectation is that maybe within self-dual gravity they might, but I haven't tried that because the amplitude of self-dual, there's only one amplitude in self-dual GR of just positive helicity gravitons, and that is very complicated.
So we don't know what the interpretation is.
Not in the bulk level, to my understanding. We know this Twistorial interpretation, and we know the interpretation in self-dual GR, where these things actually get completed into genuine global symmetries of self-dual GR, but I did not tell you what self-dual GR is, so I don't want to press on that too much. Unless you can ask me in the discussion session, of course. These are genuine global symmetries, and these currents then become basically holographic imprints of those global symmetries. In the full GR case, we do not know if these are global symmetries of the bulk. They are not global symmetries of the bulk theory, because GR is not integrable. If you had infinitely many global symmetries, then Einstein's equations would tend to become integrable. But they are not there. In the boundary, who knows what happens? The Twistorial description seems to support these symmetries, and if there is a there's a mysterious Twistorial description of full gravity, then it might support these symmetries still, but that's still missing just as much as celestial CFT is missing.
So, Atul, what is superrotation? These things with this SL2C superrotation be related also to the deepest superrotation proposed by
I suppose that was, well, I have only learned them by talking to you guys, but I'm assuming you turn on a Z-bar dependence and then make arbitrary diffeomorphisms, depending, smooth diffeomorphisms rather than holomorphic diffeomorphisms. These are not related to those. These are genuinely symmetries of twistor space, and I don't think that's a.
This structure cannot hold in that case.
Yeah, that extended diff S2 doesn't appear as a symmetries of this twistorial viewpoint. They're not bulk symmetries of subdual GR either. At least these ones are genuine bulk symmetries of subdual GR, if not full GR. Diff S2 is not even that, to my knowledge. Or maybe nobody has tried. I'm not entirely sure. Too much symmetry makes a theory trivial.
Not interesting.
It's not too much? Okay, good. Let me quickly do the Yang-Mills case. If people haven't... Oh, never mind. Okay, so in the Yang-Mills case, you have to introduce an auxiliary... Well, you have the action that I wrote down earlier. But you have to augment it by a current algebra system, so S current. You have to augment it by an extra Kac-Moody current algebra with generators. Level 0 Kac-Moody, as Prahar was discussing yesterday. Use JA of Z with OPEs coming from the structure constants of the gauge group that you're trying to mimic. So what I'm going to do is I'm not going to put an H bar in this OPE so that I can keep the graviton impurities away from the pure gauge theory OPE. At the end of the day, this is still a model, and hopefully we'll be able to take all of these impurities into account into some single Einstein-Yang-Mills theory in the future. How do you define a gluon? A soft gluon operator is now defined as capital J A Mn of Z equals J A of Z mu1 dot to the M, mu2 dot to the N, all normal ordered, so evaluated as Z. Of course, the J's don't have any OP with mu1 dot and mu2 dot. I'm going to take a separate decoupled current algebra system. Now, the hard ones. And this is a Lie algebra index. And the hard gluons can now be determined by exactly that kind of sum that worked for the gravitational case. And that just gives you the current times a vertex operator e to the I mu of Z capital. If you're familiar with 2D CFT literature, like DeFrancesco, the big yellow book, then these objects, these exponentials are known as vertex operators. In any case, now you can basically easily see that the leading order in H bar, since I haven't put an H bar here, the OP of the hard gluons will exactly be the OP of these currents. And any OP that I have between these exponentials will be subleading. Presumably, if you also consider the OP of the subleading terms, then you generate something in Einstein-Yang-Mills, but that is still unknown.
Sorry, can you construct an energy momentum tensor like in the usual pseudo-Ara construction, which is in the...
Oh, yeah, this is just a beta-gamma system, so it's energy momentum tensor, it's just a standard thing. But this CFT is non-unitary, it has negative central charge, but a modulo that is just...
Right, so what's the interpretation of this energy momentum tensor and bulk? Or?
I don't know, I haven't really... I have thought about it, but I haven't really managed to connect it with the energy momentum tensor that Prahar would define as a shadow transform for negative helicity graviton, because in this sector everything is just positive helicity. I have no idea how to connect it, but of course this is a CFT, so it has its own energy momentum tensor, however non-unitary.
Because usually if you take the zero modes on the Virasoro generators, maybe integrate them over the coordinates of the sigma mode can have some bulk interpretation. I don't know.
Right. You see, I'm doing everything at the level of amplitudes. Maybe I first need to go to the space-time perspective that I was mentioning.
Actually, because then if you deal with that, you'll have to twistors coordinates, cavities, maybe something.
Yeah. I'll have to see, but I haven't been able to make any connections.
Okay.
Yeah.
I just wanted to comment on that. There's actually a paper by Steve Berger and Taylor that show that in the amplitude sector, if you take two gluons, sum over their colors, and take the collinear limit, you get an amplitude that has the exact form of a graviton amplitude, where you just so that basically looks like two of these current operators taking the collinear limit, and then you have to remove some of the collinear singularities, which is like the normal ordering prescription, and then you get some amplitude. People haven't made that precise, but there is a similar type of result on the amplitude side.
So that's unrelated to the shadow transform, the negative helicity graviton, or is it soft graviton, or is it the same thing?
In the full theory, if you have gravity and gauge theory, then the guess would be that the full stress tensor is the one that I constructed using gravity plus the Sugawara stress tensor. Which
did they show that just the gravitational one doesn't have the right celestial OP in Einstein-Young modes? Okay. I suppose that would correspond to, since I added an extra current algebra here, there would be an additional stress tensor. So you get JAMN, JB, RS, Z prime going as the little JOP generates the prefactor that we wanted, JC. Z prime, and then the mu's just add up to leading order in H bar. So M plus R, N plus S at Z prime plus order H bar. And this just gives you, this whole thing just gives you J, C, M plus R, N plus S, Z prime. And similarly, you can get the hard OP for gluons out. So that's the application to celestial CFT. And it's basically ongoing research at this stage. We have been building these basic models. Can we get some brainy characteristics from these? Basically, can we get these models as D1 brane world volume theories by wrapping D1 branes in twisted strings? And which twisted strings? We need to take very specific twisted strings which don't have any target space anomalies and stuff, so that we get a well-defined quantum theory. And the hope is that over the coming years or so, we'll have some sort of a concrete realization that completes this picture.
You're saying that these models can be realized as for volume theories of D1 and not one of the fundamental string in the S-dual frame? So usually for Western Innovator models, you need some NS flat background, so I would be surprised to see that this is for the D1. Maybe it's an A comment.
Why would you be, sorry, could you repeat that?
You said that, maybe
so you would be surprised because?
You want to realize this as for volume, sigma models
of a D1.
Volume of the D1s instead of fundamental strings?
Yes.
Why the D1s and not the fundamental strings? The Ramon background is usually, it's a bit of a mess dealing with this. So maybe in the S-dual frame, which have fundamental strings, is naturally a Western Innovator model.
Well, maybe we didn't think about doing fundamental strings because D1. We're just trying to mimic the Maldacena case, where you have D3 branes and you try to realize n equals 4 as a world volume theory of D3 branes. We're just trying to mimic that. Does this S-dual viewpoint help there? Maybe we can try something analogous.
But not sure understanding. We can discuss probably.
Yeah, I don't really know that much about it. I'm just learning string theory, so we can discuss. Yeah, I would love to discuss. I'm so basic. Anyway. Yeah, it's 11:30 exactly.
Will there be 5 minutes? Or
Up to you.